Thanks very much for tuning in. Today we've got a really interesting chat with a great AWS partner, Zenotech, and we're going to be talking about the development of next generation CFD codes. I'm Neil Ashton. I'm a principal CFD specialist SA here at AWS. My background is, a mixture of academia and industry, developing, CFD methods, and now trying to see how, AWS can play a role in improving and developing the CFD community and what people use. So maybe if I want to introduce who else is here today. So Jamil, if you want to introduce yourself.
Yeah, so hi, I'm Jamil Appa. I'm co-founder of Zenotech. So my background is in CFD and I suppose computational engineering in general, with an aerospace focus as a background. But today, yes, so Zenotech is a bit wider than aerospace today. Mike?
Yeah, my name is Mike Turner, so I'm a product lead at Zenotech. My main areas of focus are on kind of high performance computing and cloud infrastructures.
Cool, and maybe you could give everybody just a bit of a background on Zenotech.
Yeah, so as I said, we've got a background of aerospace previously before setting up Zenotech. So we set Zenotech up in 2012. We're based in the UK, in the west of the UK, in a city called Bristol. And our focus really is on computational engineering. So we develop our own software and we deliver that on cloud platforms, which we'll be discussing today. And we are active in delivering those capabilities into the aerospace sector, which is our background. Civil engineering, so the built environments, the buildings, renewables, so things like wind farms, and automotive sectors, which is becoming increasingly driven by simulation. So we've got two main products. I'll quickly introduce ZCFD and I'll hand over to Mike for Epic. So yeah, so ZCFD is our Fluid Dynamics, our CFD software that we've developed from the ground up, really to take benefit of the underlying computational architecture changes that's been happening. So it's many core capable, and it runs on the widest variety of platforms that sort of are out there today. So we're very much focused on performance. Algorithm-wise, we haven't developed anything new. We're just using the best-in-class algorithms for the different sectors that we're working with. And with a focus very much on accuracy and performance. And what I mean by that is sort of the industrial performance, which will quite happily compromise in some areas of accuracy, if it allows us to deliver capability or results in an appropriate time for industry. And as I said, it's been engineered very much to take benefit of the latest sort of computational architecture changes that have been happening in that industry. Mike, do you want to describe Epic?
Yeah, obviously, yeah. So Epic is a kind of second product, came after ZCFD. So obviously developing a CFD code is quite computationally expensive. You need generally big computers to develop and test on. And as a small company, we didn't kind of have the capital to just buy a supercomputer. So we started using the academic computers in the UK and also the cloud providers to kind of just use computing and HPC on demand as and when we needed it. And that worked quite well for us, and was also a kind of a fairly common request from our initial customers. So we took what we were doing and customer requirements and developed that into its own product, which became Epic. So it's really a kind of a portal for job submission and data management that allows our users access to a wide variety of on-demand high-performance computing, both traditional supercomputing and cloud-based HPC. So that's Epic in a nutshell.
Cool. Yeah. Well, I mean, that's kind of the product placement over, right? I mean, now, I'm always really interested, and obviously the title today is kind of next generation, code development, and I really like, in a way what you've done, because it's really interesting to see, has there been a plateau? Is it now that finite volume code, second order unstructured grids, is that it now, and it's just a matter of making things quicker or maybe getting benefits from hardware? And I always used to see many presentations at CFD conferences talk about GPUs and the potential for it, and it seemed that it was kind of slow to see something that could take advantage of that, but also be robust to run cases. So, what drove you to go down that route, from the beginning? What was it that made you think, no, we've got to have a code that can support this kind of many core GPU technology?
I suppose best place to start actually is to wind the clock back to, I would say, even 2004, so the mid 2000s, when multi-core first made an appearance. We were sort of hitting the peak of the single core frequency scaling, or hitting those kind of limits, and the silicon industry then decided to, well, rather than making the chips go faster, we'll actually just put multiple chips on the single slab of silicon as the gate sizes shrank, and that had an immediate effect on the kind of performance that we'd have. So CFD itself, so CFD algorithms themselves are typically memory bandwidth bound, and especially when we're talking about unstructured algorithms, and the main reason being is we're dancing around in memory all over the place with unstructured. There's no structure to how things are laid out, so you can't try and sort of stream things into a processor in a nice structured manner. So you're always jumping around in memory, which sort of caches do help, but it will still, your jumps tend to be bigger, much bigger than your cache lines. So you're going to be memory bandwidth bound with those types of algorithms. And the reason for using those types of algorithms is they're important for industry. So from an industry point of view, where we're making use of CFD, the only real way of making use of it practically is to use these unstructured algorithms, because otherwise the cost of generating meshes it just takes too long. So unstructured is what it is. It's memory bandwidth bound. And the computer architecture was pushing us down the route of multi-core, which ultimately the memory bandwidth per core was going down, and that has been the case on that type of silicon since that point, to be honest. And about the same time, there were various sort of activities which I suppose predated that in terms of using GPUs for computation. So there's lots of interesting work out there where people sort of use a lot of the texture mechanism in GPUs to actually do computation. But again, that computation tended to be very structured in nature because textures tend to be structured. But NVIDIA launched the CUDA architecture in 2005, and we started exploring with that technology at that particular point, because that looked like a way forward to try and get through this bottleneck that we were seeing coming up with the advent of multi-core. So that sort of pushed us in that, and there were other things happening at the same time. So there's another company in Bristol called ClearSpeed, which were making again a different type of multi-core processor. So there was lots of activities here locally in Bristol in the UK, which were sort of reviving the interest in looking at different architectures. So we sort of started sort of actively looking in earnest at trying to exploit those architectures for something which is computationally intense, like CFD, but with the specific features of unstructured, which means jumping around in memory. So that was sort of initially drove us to start looking at those types of architectures.
And how hard is it to develop a code that is able to work on on GPUs, many core devices, as well as traditional CPUs? What if someone's out there trying to adapt their code or develop a code, what did you have to go through to get to that point?
I suppose to still start off with is sort of you've got to understand your underlying algorithm. So what can and can't you do to get your algorithm to work? So you've obviously got a mathematical algorithm which you're trying to encode. it's getting to the heart of that, and ultimately it's around exposing parallelism in your algorithm. So you've got to write your code. So you decompose your algorithm into sort of the unit steps, which can be executed in parallel. And in unstructured, it's a little bit more challenging than just sort of breaking that down, because the way that the algorithm tends to operate is that you tend to what we call sort of gather scatter in algorithm speak, where we're gathering some data from two different memory locations. We do some computation, and then we scatter that data back out. But if you imagine the case of scattering, you've got to make sure that the data that you scatter back out, you haven't got another parallel process scattering to that same data location as you are. So you've got to make sure that those types of conflicts are dealt with, and not just dealt with from the point of view of using things like locking or atomic locks to make sure that those updates are atomic, because relying on those types of features will just slows down your algorithm. So you've got to come up with techniques. And interestingly enough, actually, there's a lot of the techniques that you end up using are the kind of techniques that we used to use on basically the highly vectorized craze in the 80s and 90s. A lot of those techniques have effectively come back into fashion again, because there's a lot of those things that you end up having to use when you're trying to program these algorithms on devices like GPUs.
But why do you think more codes are doing it? Why has this not become the new standard, I suppose?
I suppose in one sense you've got to start afresh. You've got to start with a clean sheet of paper. I think that's one piece. And a lot of codes out there, whether they're open source codes like OpenFOAM or the big OEMs like the Ansys's, and the Siemens of this world, have got quite a large code base, and the cost of them effectively re-implementing that for GPUs is huge. So I'll give you an example. So Ansys's approach to this has been very much to use is to offload the linear solve. So they make use of NVIDIA's linear solver library. So they will just offload just the linear solve portion onto GPUs and bring the result back onto the CPU, because that can be defined with a relatively simple interface, because that's the only algorithmic piece that you're offloading. Not many CFD codes in terms of the algorithms we use today make use of sort of dense linear algebra. So where you've got sort of BLAS type routines, which the likes of NVIDIA already provide for their GPUs, it's not something which CFD codes would use naturally. So to get the best out of these new architectures, you've got to think of trying to get as much of the CFD solution algorithm onto the GPU. Otherwise, yeah, you rapidly hit into bottlenecks. So Amdahl's law comes and bites you very quickly. And then you don't really realize the benefit, the full benefit of these architectures. As an example, I suppose you look at the like of sort of machine learning and AI community. A lot of their algorithms are posed as dense linear algebra, so they just make use of just the BLAS routines which are provided off the shelf, and hence why they get the massive accelerations that they do, because actually most of the work is just dense linear algebra, or it can be posed as dense linear algebra. Whereas CFD is a lot more complicated. So you really have to start with a clean sheet. But saying that, today we started with a clean sheet sort of in 2012. There's lots of frameworks that you can use today to actually take a lot of the mundane work out of starting off with a clean sheet. So the complexity of talking to these different devices and managing the different memory hierarchies that you have. A lot of that's got a lot easier now with a variety of different frameworks, whether they're the frameworks from the CUDA framework obviously has evolved over time, but you've got projects like the Trinos project out of Sandia, which provides some higher level abstraction to various architectures, which can be used to help that along the process. So we effectively, because we didn't have anything else to start off with, we rolled our own, but it is getting easier.
But do you think there's, is there any, you're talking about, kind of moving linear solvers over. Is there anything that needs to be done extra in the sense, the classic implicit multi-grid type approaches that many of the large commercial codes are using, and you start to look towards, higher fidelity methods, LES methods. Does that play even more into the strengths? If you can go explicit, is it the case that as we move towards LES and beyond, that GPUs become even more the right choice, essentially?
Well, so explicit methods tend to parallelize more naturally than implicit methods. So implicit methods typically have parallel bottlenecks, and it typically comes down to sort of the types of preconditioners that you might want to use in solving in a linear system. And they tend to not parallelize very well, so you end up at some bottlenecks on the when looking at implicit. Well, they're saying that there's a lot of research going into trying to find ways around those kind of bottlenecks, because it's going to be important if we really want to exploit these exascale systems which are coming up, or nearly up pretty much with us. And so the algorithms haven't quite caught up to make use of those types of size of system. Saying that, explicit algorithms definitely will scale up to onto the exascale type systems, because a lot of their operations are local. I think the challenge comes with as you increase in scale, is this issue of compute intensity. So for today, for our finite volume algorithms that we tend to use today, for every memory access that we make, we're actually not doing a lot of computation. So our compute intensity per memory access is relatively low, and it's actually very hard to increase that in a finite volume algorithm sense. So one of the ways of trying to get through some of these bottlenecks, and when we were talking about memory bandwidth bottlenecks, is for every memory access we want to do more work. So we want algorithms really that we can that will work harder for each data point that it accesses from memory, and some of these high order techniques actually start to deliver that. So for every memory access, you end up doing a lot more computation. So ultimately, that means better performance, because they're not so bound by memory bandwidth. They're still bound by memory bandwidth, but not as much as finite volume, and that ultimately allows us to scale better as well. So we've got a capability of being able to use what's called discontinuous Galerkin flux reconstruction. And the best way of describing it is it's a hybrid between high order methods and finite volume, in that you have your operations are still very much per cell or per interface between the cells, as you would do in a finite volume sense, but you do a lot more computation per cell and per memory access. And a lot of the computation that you do in that sense tends to be back to sort of dense linear algebra as well. So you can now start making use of some of these the kind of libraries which have been used for AI and machine learning to access the true performance of some of this of some of the hardware. So that's sort of the direction of travel, I think, when it comes to sort of algorithms. And as you pointed out, so that allows us then to push forward in terms of these scale resolving type techniques, so whether they're LES and there's a variety of hybrid RANs, LES types of capability which is out there. But yeah, that brings that all into scope from an industrial point of view.
Yeah, I mean that's why that's why I'm quite excited really to show the sort of work that we've both been doing together, because I've read a lot of papers and talk about the relative performance of certain codes or GPUs or high order or et cetera, and the big one is obviously price performance as well. And ironically, I mean, it's the cloud that kind of brings that clarity, right? Because the public pricing nature of everything you can easily compare, and you can run these benchmarks across all these different hardware types, GPUs, CPUs based on Intel, ARM, you name it, and actually see what is the performance and also the price differences. So maybe it's interesting if we move on to some of the work, and maybe Mike, you can kind of introduce the work that we were doing together to generate these sort of graphs.
Yeah, sure. Okay, so this is a CFD test case from Airbus called XRF1. So this is it's a non-production aircraft from Airbus, but it's as close to a production aircraft as you can get without being a production aircraft. So as a kind of a testing activity, we took the XRF1 case and generated a few different meshes on it, and then ran it on a variety of platforms just to check the performance. So we picked several different AWS instances, and we also had a kind of an on-premise x86 Cray CS400 based machine with InfiniBand interconnect as a kind of a baseline, as a representative of what someone might run it on an in-house cluster versus the cloud options. I can remember we tested a variety of instances. So we did some of the C5s and C5Ns. We also looked at GPUs, and we also looked at the Graviton 2 processors. So I guess the graph on the screen now there is giving us the iterations per minute for a variety of those options, with the orange being the baseline Cray machine, and then you can see the C5N, and then the green are the GPU options. Oh, actually, sorry, the blue is also a GPU option there as well, isn't it? So it was an interesting study. This was a 149 million cell case, so a relatively chunky case, probably larger than would be run on an industrial day-to-day basis. But we did it just to really push the scale. So we scale up to 100 nodes, so 3,600 physical cores on AWS, and 100 nodes on the Cray as well, just so we could compare some strong scaling figures.
Yeah, and I mean, maybe we should just for people who are not fully aware of all the kind of naming conventions. I mean, the C5N 18x large is the Intel Skylake 36 physical cores, I think around 192 gigabytes of RAM, which is based upon the networking is on the EFA, the Elastic Fabric Adapter, that's kind of giving that that good interconnect, and then the P3 of the two different sizes here is the NVIDIA V100s. So the largest one, the 24x large, has 8 of them on a single instance. And then interestingly, the G4DN is the NVIDIA T4. And it was quite interesting, at least from my side. I mean, if you took away the GPU results, you'd be like, okay, that's nice to see. You're seeing that good performance on a cloud platform versus on-premise. But actually, I'm used to seeing that. I'm used to seeing that we deliver good performance against kind of on-prem CPU. The really interesting bit for me is the GPU performance. That's kind of super interesting. And maybe actually I should show the second graph, because most people seeing this graph now would think, okay, the GPUs are faster, and you can scale out more. Though you're never going to get that iterations per minute with a CPU, because if we extend that graph to the right, it's never going to get as high as that P3DN will. At some point the scaling is going to drop off. But I think the kind of really big one for me was the price. When you take the kind of public pricing that you can find on the AWS website, the fact that not only are the GPUs all faster, but they're also cheaper. I mean, that's really interesting, isn't it?
You win on both fronts.
Yeah. It was, and I also agree about the G4 as well. Was an interesting surprise for us. Previously, we hadn't really we've been kind of drawn to the P3s and the shiny V100s. We hadn't before this exercise haven't tested on the G4DNs. So it was, yeah, when you bring the price of those in versus the price of the P3s, it's quite a compelling argument.
Yeah, do you think, I mean, I've not actually seen this too much before, because I think, I've read some papers where people compare, but they've not really been able to do that. I mean, do you think that in particular, GPUs, there's a relevance to the cloud for GPUs just because they are relatively expensive things to buy, and particularly if you want to test things? Do you think almost that there's even more incentive to move to the cloud if you're doing, if you need this many GPUs for your simulations?
I think so, yeah. Definitely, as you say, getting the latest GPUs is expensive, and the cloud gives a couple of advantages. I guess the kind of the on-demand nature of it means you don't need these GPUs sitting around when maybe all of your codes can't make the best use of them. So obviously, if only one of your codes can use them, you probably don't want a whole cluster of them. And also, we tend to see that they make it into the cloud providers before they get into the standard kind of HPC data centers. So you get earlier access to the latest hardware as well, which is quite good.
And it also gives you access to the ability to get access to the scale as well. I suppose, as Mike, as you were pointing out, this issue of the high unit costs of GPUs, to make a business case to have an internal system with lots of them tends to be quite challenging, because there's only a few codes which will use them. And when you do need to use them at scale, actually, yeah, as you said, the cloud is pretty much the only way of getting access to them at that price. And interesting enough, some of what's underlying some of the performance that you're seeing, it's just it's the same example of this idea of increasing computation intensity. So what you're doing with the GPUs is you've got a lot of computation happening within a single node. So to get your turnaround, so typically from an industry point of view, a lot of this is metricated by turnaround time. So it might be let's say for an aerospace, typically you want your jobs to be turning around within a couple of hours. So you tend to run on the number of processors or GPUs or whatever that will give you that kind of turnaround, because that will give you the ability to churn through all the jobs that you need to do. But by increasing the computational intensity, actually it is better, because then actually we're not losing in terms of the effects of scale. So in a lot of these parallel jobs, the more processors you run on, the less efficient your algorithm becomes. But by keeping the computational intensity high, we don't actually have to run over that many nodes to achieve the kind of performance that we have to deliver these sort of 1 hour turnarounds. So that plays into the hands of GPUs as well. So you've got, and as you pointed out, Neil, you win on two fronts. You win on both time and cost. So it's a bit of a no-brainer.
Yeah, exactly. I mean, there's a couple of, I think the other, so this was the large test case, wasn't it? This was the 149, full aircraft, big case, which I suppose some companies, would run. But I know that there was also some work done on the kind of single node performance for a much smaller case. And, I think this did show the, quite substantial speed up of the GPUs compared to the CPUs and the on-premise. But I think the one extra angle here that I think is interesting to show is the Graviton 2 performance. I mean, I don't know, how do you see as the kind of ARM angle to all this? Obviously, the GPUs is a kind of really exciting, faster and cheaper, but yeah, it seems like ARM is a very interesting one, given for this test case, it's similar or even slightly faster performance than the equivalent Intel CPUs here.
Yeah, I suppose one thing to point out, though, is the on the Graviton, we didn't really do any real sort of ARM optimizations. I suppose this was effectively code that's been running on x86, compiled with the ARM toolchain and run to give those kind of results. So there's probably more to be had in that. I suppose the other point to make, I suppose, again from an industrial point of view, as Mike sort of pointed out, the different codes have different sweet spots in terms of the architecture. So, for example, today there aren't any mesh generators, for example, that run on GPUs. There's some parts of the post-processing algorithm which are starting to run on GPUs, but vast big parts of that still are very much CPU encoded. So I think if you look at the whole sort of tool chain which is used within simulation, you need a mix. You need to be able to mix and match, and what you want to be able to do is then pick off the best architecture for each particular stage that you have to give you, because ultimately, from an industrial point of view, what you're interested in doing is actually shrinking down the time it takes for that whole process, not just one part of it. Otherwise, again, Amdahl's law comes and bites you. So actually having access to a variety of architectures is actually very important, so you can get the best fit, and allows you to deliver that. So yes, they all have their sweet spots.
Yeah, and I suppose that's ultimately why, AWS, we like to say that we have the broadest set of instances, because every code, as you say, has a different sweet spot. So whether it's using standard MPI or OpenMP or CUDA, you can't just pick one, right? It's nice to have the options. So that one particular code, or as you say, even the mesh generator, you need to run on a certain platform. It's kind of nice to be able to mix and match them, rather than just sticking everything on a single one and having to just take that. But where do you see things going then in the next 10 to 15 years? I feel like you've perhaps been ahead of the curve with the development of your code supporting GPUs and ARM, and as well as your standard x86. Where do you see things going in the future?
I think we're going to keep on seeing sort of, and NVIDIA is sort of going down that route of having increasing specialization on chip. So you'll have whether they're the ray tracing cores, for example, on the latest NVIDIA, the RTX cores. Again, it's something that dense linear algebra can make use of. Again, the focus on AI and machine learning. But if we start making progress in terms of algorithms, moving in that direction, we'll be able to make use of those. But I think where it comes sort of overall, it's starting to mix those things together. So I think especially after what the world's gone through this year, I think the green agenda might come back again. So the performance per watt, or actually sort of in terms of from an industrial point of view, again, it's going to be the result per watt, if we want to sort of phrase it that way, is going to become important. And we've already been asked those kind of questions from some of our customers, that's going to be an important metric from an HPC point of view that they need to be able to report on. So they need that's going to be one of the driving pieces. And I think the push algorithmically in being able to support exascale is going to have an impact. So there's going to be some sort of flow down to more general, both from an algorithm point of view and from a hardware point of view, from some of the exascale efforts which are going on. And I think that's going to have an impact as well in the direction we go. So I think algorithms are going to change, and I think we need to stay agile and flexible to be able to pick those up as they come along. And I think, like all CFD codes and a lot of algorithms, they ultimately have a shelf life. If we wind the clock back to the kind of algorithms which we used in CFD codes from back in the 80s, are definitely not the algorithms that we're using today. So we need to stay on top of that. And as technology progresses ever rapidly, algorithms are going to have to change rapidly as well to make best use of where the underlying hardware is going. So agility is going to be key to be able to exploit where the technology is going.
And how do you see it on the EPYC side, Mike? I mean, do you see a lot of your customers kind of moving to the cloud to basically just take advantage of being able to get this variety of different hardware, the latest hardware, and not have to kind of bet almost, on a certain thing. How do you see the development of the kind of Epic platform over the coming years?
Yeah, we definitely see that as a kind of a key advantage of doing it via something like Epic, where, as new instance types are released or new architectures come online, we tend to kind of test the codes out and then make them available to our customers, and the new instances or the new clusters just pop up. So via a single interface or single API, they don't have to make any changes on their side. It's just available. As prices change or new clusters become available, it becomes more of a dynamic marketplace. So they can pick whether cost is their driver or turnaround time is their driver. There's a resource for them, and we're just doing our best to match them up, really. So I think that's going to continue. Obviously, more organizations moving to the cloud now, but there's always people wanting to make sure they've got the ability to switch out, if their business changes or needs to change and they need a new resource type, they want to make that as easy as possible.
Yeah. No, I definitely see, and I'm kind of hoping that some of this work that you've been doing will kind of nudge people to see this. One, that actually being able to have a code like yours that can adapt to different hardware actually is a genuine advantage. The fact that we've been able to essentially just communicate and say, hey, do you want to try this GPU or do you want to try this ARM? And you just say, yeah, okay, just compile the code and go run on it. For some people that would be a month or a year effort to port their code over, where you can kind of do it. So I suppose not knowing what's coming down the line, having a code that can stay flexible, it seems to be quite a key thing. So maybe one thing that we didn't point on is, what about all the other bits? I mean, this is the CFD kind of core bit, right? But how much is there needed for the meshing and the post-processing to also take a step change? I can see your code can take it, but the fact that you said about, the meshing tools, do you think that is in need of a kind of a revolution to keep up with the solver technology, essentially?
I think very much so. If today we really wanted to exploit an exascale machine, we wouldn't be able to, because we wouldn't be able to generate a mesh big enough. If we're talking about sort of an unstructured mesh big enough to fill an exascale machine. So in some sense, exascale running a single simulation when it comes to sort of the world of unstructured CFD is probably it's just not possible, because we haven't got the technology to be able to do that. So saying that, there's various activities happening within the UK academic circles within various universities, looking at actually what would be needed from a mesh generation algorithm to work at exascale, and that's irrespective of the underlying hardware. And then the next piece you sort of take from that is, okay, if they do come up with an algorithm, how can you make it used? Because a lot of these exascale machines are looking at being based on accelerators, whether they're from Intel or from NVIDIA or from AMD. That's where they're going to achieve the exascale performance from. We'll have to then try and match those through. I suppose one of the saving graces, I think there's a lot of developments, whether they're GPUs or even some of the algorithms which are used today, which has actually been driven from the gaming industry. So the hardware, there's a lot of it's been driven by where gaming is going from, and actually there's a lot of algorithms which are being used in some of these ever complex games, which actually do use mesh generation techniques, and a lot of the libraries which underpin some of these more complex games I'll start to sort of point you in the kind of direction where you could see that coming from. But we definitely need new approaches to be able to do that. And the same, as you said, from a post-processing point of view, a lot of the algorithms sort of are very much conceived as being single-threaded. We need to think about those again. So there's a lot of brain power required to further those algorithms, so that we can keep on making use of some of these stuff harder. And an example is, I suppose, if you take the kind of turnarounds that we can get on these GPUs on the solver, you'd probably be able to outstrip the time it takes to generate some of these more complex meshes. You can get answers back quicker than it takes to generate the mesh, and that then starts becoming a bit of a big bottleneck, in the sense that I know I can get answers very quickly, but now it's taking me 10 times as long to generate the mesh before I can get the answer. Then that points you to where the next bottleneck is. But that tends to be the way we go. We tend to we can focus on one thing, speed it up, and then I suppose it's Amdahl's law again. We then focus on the next bottleneck and look at that. And as I mentioned, exascale is probably going to be the one that drives it.
Yeah. Well, I mean, that's been super interesting chatting with you both. I mean, I feel like we could probably go on for hours and talk about many other topics that we didn't include. But yeah, I think it's, in summary, I suppose it's interesting how the development of these new methods is very much a kind of a marriage of hardware and software, right? We can deliver this infrastructure, on AWS and give you the ability to do it, but you've also got to have the software, and you've got to have the codes that can take advantage of it. So it's that's why I think this has been a good example from you guys, that because you have the solver technology, you can take advantage of the hardware. And yeah, it'll be very interesting to see how the next few years pan out, and whether there's a revolution in CFD methods and things accelerate. Yeah, I look forward to finding out. So yeah, thank you both for taking the time, and look forward to continue working with you and Zenotech.
No problem. Thanks, Neil.
Thanks, Neil.